scenarios here. We have a base of 2, a base of -2, a base of 1/2, and a base of -1/2. All right, I want you to think about this. The other day, we did a finite geometric sum, which means geometric, you're multiplying by the same thing over and over again. Finite, it has an end, and we add them up. So we had this lovely formula. The sum of the first n terms of a geometric series is g sub 1. 1 minus r to the n over 1 minus r. Now, I want to investigate what happens in terms of r in 4 different situations. So a positive number greater than 1 raised to the n. I want you to think about in your brain as n gets larger and larger and larger and larger and really big number. Think about what that does to the total.
Increases it.
Yeah, it's going up like crazy.
Hey.
When we graph these, our graph look like, come on, Moby, show off. There you go. Woo! Exponential. Goes up forever and ever and ever. So, can we?
No.
Isn't it on the denominator?
Oh, it was an R. Thank you. So that's what it does. It goes up like that. All right. This one, interesting. Negative number to a power. If we do that to an even number, it becomes positive, right? If it's raised to an even number.
Yeah.
But if it's raised to a negative number, it becomes
Negative.
Positive.
weird. Let's just plot some points and think about what that graph does. So if we do it to the 0, anything to the 0 power is 1, right? But if we do it to the first power, it is -2. But if we do it to the second power, it is positive 4. If we do it to the third power, it is -8.
Wow.
If we do it to the fourth power, it's positive 16. Look at it.
It's like a little
It's going
tornado.
like this way and this way.
It's a tornado.
Crazy.
Wow. Wild. So
So it's getting infinitely large over here on the evens, but infinitely small over here on the odds. Do they cancel? Think about it.
think about it.
Just think about it. All right, you got a question.
Yeah, so like, does it mirror perfectly then?
No, it doesn't. It's not perfect. Because this is 1, this is -2, this is positive 4, this is -8.
Okay.
It doesn't perfectly mirror. No. All right. Now, let's think about 1/2. As n gets infinitely larger. So we think about that sequence as we get bigger and bigger and bigger and bigger, as our position increases. What happens to our value? It decreases. Like, pull out your calculator. Let's try something. One half to the fifth. Raise 1/2 or 0.5. Same thing, guys. 0.5 to the fifth power. 30 seconds. 1/32. Or what? 0.03125?
Mm-hmm.
Okay. Now let's do 0.5 to the 10th power.
Ooh, it's very wee.
It got smaller, and there's an e to the -4, so we've switched over to scientific notation.
Yeah.
All right, let's do a huge jump. Let's do it to the 100th power.
Very close to the same.
Bless me. 7.8 to the -31st.
We got -31st in our scientific notation. E to the -31st, so that's like 10. We have to move that decimal 31 times.
So what?
There's a little bitty number in it, because it's 30 zeros before we ever get to that first number. All right, let's do it to the 1000th power.
Oh my goodness.
It says 0.
This is
Now,
illegal math.
is it truly equal to 0?
No.
No.
That's just too small.
But in effect, it's 0. It is what we call approaching 0. when I raised it to a power and increased that power. And as that power gets infinitely large, the value of the fraction really is almost 0. Okay, so what does that do to this? If I raise that rate of 1/2, that ratio is 1/2 to an infinitely large number, it's like 0.
So that makes the whole equation.
It kind of goes away, doesn't it? If it has a value of 0, this part of the equation has a value of 0. And what is 1 minus 0? 1. And what is 1 times g sub 1?
The same number as you started.
G sub 1.
Yeah.
And guess what this formula is for? The sum of an infinite geometric series. Now, it didn't work here
Because he's higher.
because it didn't turn to 0. That ratio to the n on this one was not 0. This ratio to the n on this one was not 0. It did work here. Now, while I'm passing out today's notes, I want you to think about, does it work in the 4th example? Think about it.
Think about it. Close your eyes, dream about it. Make a daydream. Hey. You're a mathematician.
Julie, what do you want to do when you grow up?
Is that where it turns into a diagram?
How about for a job?
It doesn't actually but it's so small.
You're gonna be a stay-at-home dad?
All right, I am recording.
Yes.
Look at this. Is that nobody was here today? No, nobody was not here today.
When the absolute value, so yes.
Yes, it does.
Because when R is
Okay?
the absolute
So,
value.
this works for these two because, as you can see on your notes you just got, it's for values where the ratio is less than 1. Now, the absolute value is less than 1, which means between -1 and +1. That's what this means. So if the absolute value of the ratio is between, well, if the ratio is between -1 and +1, we can find the sum of an infinite geometric series. Now, that's the only time we can. If the ratio is greater than 1, or if the ratio is less than -1, this part of the formula does not go away. So we can't do it. So it only works when R is between -1 and +1. So on this one, what is R?
It's greater
3
than
halves.
1.
Can we do it? No. On this one, what is R?
3.
1/3.
1/3. Dividing by 3 is the same as multiplying by 1/3. So can we do it?
Yes.
Yes.
9 over 1
right.
minus 1/3.
So how do we do it? The sum of an infinite geometric series is easier than a finite one. It's the first term over 1 minus the ratio. Okay, so it's 9 divided by 2/3, which is 9 times 3 halves. It's 27 halves, which is 13.5. Is that what you got? You can use a calculator. I can too, when I want to.
Is it just faster for you to do in your head, Miss Williams?
Yeah.
What's 40 divided by 0.4?
Wow.
Why? We don't have to do that.
I have no idea.
Oh, my
We do.
calculator did not like that.
We'll do something close, but 40 divided by 0.9. You'll see in a second.
Okay,
All right,
well,
this one.
What is 40 divided by
What is the common ratio?
12?
100th, right? Or 0.01. Because we got to move that decimal twice, right? So that's the ratio. Oh, it's 40 over 0.99.
Whoa.
So can we find the sum?
Yes.
Yes. We can do it because this ratio is in this interval. So it is possible. It works. So the sum of this infinite geometric series is the first term, 40, over 1 minus 0.01, which is 40 over 0.99. All right, which is 40.40 repeating. Do y'all see that repeating part? Generally, when something's repeating, I would not write it as a decimal. I'd just switch it over to a fraction on my calculator. Do you know how to switch it to a fraction on your calculator?
No.
Second.
Hit math, fraction. This is your button. This is just enter, enter.
I hope I have.
Math, enter, enter. Because fraction is choice 1. Math, enter, enter. Math, enter, enter. And it switches it to a fraction, and the fraction is 4,000 over 99. Which we could have just done right here by going, right? Right. All right, number 4. What is the ratio? 1/2. Can we do it? Yes. All right, so the sum of this infinite is 1/3 over 1 minus 1/2.
Oh, wait.
So it's 2/3. 0.6 repeating.
Oh, I thought it was. Okay, that explains it.
All right, number 5. Can we do it?
No.
No, you're right. It's not geometric, is it? I want it to be geometric, but it has a problem.
It just isn't.
It's just weird.
This should be negative if it's geometric.
Yeah.
So it's not even geometric. But even if this were negative, my ratio would be -3. So can I do it?
Yep.
No. So if I fix that and make it negative, it's now geometric, but I still can't find the sum because the ratio does not fall between -1 and +1. Not possible. It would be one that looks like this crazy one that goes up and down, but doesn't cancel out. Yeah. All right. Number 6. Ratio. What's the ratio? Okay, if you have no idea, that's fair. You can always take a term like 1/3 and divide it by the one in front of it. What is 1/3 divided by -2/3? Use your calculator.
Oh, I don't know if that's.
-0.05.
I don't know if that's right.
-1/2.
Yeah.
That is true. Because if I multiplied this by -1/2, it would become positive. The 2's would cancel. I'd get 1/3. If I multiplied 1/3 by -1/2, I get -1/6. Yes. All right. Can we do it? Yes, you can. The ratio falls within the interval. So the sum, the infinite sum of this geometric series is the first term. And 1 minus r. So -4/3. All right, so with our arithmetic and geometric, there's only one infinite series that we can sum. And the infinite series that you can sum is only a geometric series if the ratio is between -1 and +1. We cannot find the sum of an infinite arithmetic. We cannot find the sum of an infinite geometric if the ratio is greater than 1 or less than -1. It has to fall in this range. So there are very few that we can actually do. All right, let's take a look at number 7. A force is applied to a particle moving in a straight line such that each second it moves half the distance it moved preceding. All right, this is where we get where theory and reality don't quite meet. In theory, if I moved half the distance every second, in theory, would I ever make it to that door if I was walking?
No.
No, I would never make it there. But if I did do it, would I actually make it to the door?
Yes.
Yeah.
It would take you so long.
Yeah. But if we measured it out and I said, okay, I'm going to take a 4 feet. That's pretty big, isn't it?
Jump.
I don't need to jump. I got long legs.
I don't think that was 4 feet.
That was impressive. I know. Now I'm just going to do 2 feet. And now I'm going to do 1 foot. Then I'm going to do half of that. Then I'm going to do half of that. And then I'm going to do half of that.
I don't think that was proportional.
It wasn't. It wasn't at all. But in theory, I never make it to the door. But in reality, eventually, I'm going to make it to the door.
We're close.
Or I'll die. One or the other. Okay?
Who is it?
So here we have this force moving in a straight line so that every second it's half the distance of the preceding second. So I'm going to draw a picture. A terrible one, because that's the only kind I can draw.
Hey.
All right, thank you. All right, there we go. So in the first second, this particle moves 20 centimeters. So in the second, how far would this particle move?
10 centimeters.
10 centimeters. Do you feel like you're in science class?
Yes.
Yeah. All right, so we keep going. So what would it would look like this. It would look 10, 20, 10, and then 5, and then
2.5.
2.5, and then 1.25. Okay, so we get it. All right, so my first term is 20. I am multiplying by something. What am I multiplying by? A half. My ratio is 1/2. So when it asks what is the total distance that the particle can move, that is asking for the infinite sum. That's what it's asking for. And this is once again where we have an issue between reality and theory and how they meet. But this is what we do. The infinite sum is the first term, 1 minus the rate. Now, I can do this because this ratio is between -1 and +1. If it were not, couldn't do it. All right, so this is a word problem. I got out 40. If I just write down 40, do I get full credit? No. It's a word problem. It must have a unit. What is my unit? Centimeters. All right, it's not going far, is it? It only went 40 centimeters.
Ford.
All right, now, okay, I don't have a super ball because that would be too distracting, but I do have this stress ball that Hosa gave to me one year.
Cool.
And I haven't used it, let me tell you. All right, so what we're talking about here is dropping a super ball. So that's the kind of annoying ball that they put in the grocery store in that little thing at the beginning when you're a little kid and you walk in and you beg your mom to buy you a super ball. Did any of your parents have the no toys at the grocery store rule?
Yeah.
Yeah, as soon as my
Especially on the
kids
toy
could
aisle.
understand, I explained that. We never buy a toy at the grocery store. That's our rule. I mean, you can ask, but that's our rule. Never. All right, so Super Bowl. We're going to drop it.
That's not Super Bowl.
No, it's not. It doesn't bounce very well either. But you're visualizing. You're imagining.
Okay.
Okay? So, what it's going to do is it's going to go straight down. It's going to hit. It's going to bounce back up. It's not going to go up as high as I dropped it, is it?
No.
And then it's going to go back down. And it's going to come back a little bit less. And then it's going to go back down and come back a little bit less. And it's going to keep doing that. We know eventually this ball is going to do what? It's going to stop. Now, if we thought about it as a geometric series, would it ever stop?
No.
No, but we know it does. Difference between theory and reality. It stops. Okay. Now. Yeah. All right. So, when we find the distance, what we're adding is that down and up and down and up and down and up and down, and up and down, and up. Until it stops. That's what we're adding. We're not doing distance like this.
What is that?
He was trying to sleep, and I thought if
No,
I
I'm trying
pretended to
to
throw
not.
it at him.
No, I'm trying
We're
to
not talking about distance lengthwise, we're up and down distance, okay? So we're not tossing the ball, we're dropping it, and we're talking about up and down bouncing distance.
Oh, I'm trying to not.
Okay, so here's my picture. Once again, probably not good. So I have the super ball. It is dropping from a height of 5 feet. So that first drop is 5 feet. That's my first drop, right? Then, it's obviously going to bounce back up. And then it's going to fall back down. And when it falls, that's my second, right? My second bounce. And then it's going to go back up, not quite as far, and then it's going to come back down. That is my third bounce. And then it's going to go up, and then it's going to come back down, but not as far. And that's my fourth bounce. And then it's going to do it again. And that's my fifth. And this time, I'm not saying infinite, I'm saying 6 times.
And we stop.
And then that's all we're adding up.
Stop.
Stop. That's right. Now, since this has a finite ending, we're not going to use the infinite geometric sum. We're going to use the finite one. So S sub n equals g sub 1 times 1 minus r to the n over 1 minus r. But guys, that gives us this. And let me change the color so you can see it. Drop, 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 drop.
Oh,
I left something out.
Raindrop.
rainbow.
I left out the bouncing back up.
Elastic potential energy.
How can I get the bouncing back up? Somebody knows.
Conservation of energy.
Destiny.
Momentum.
Destiny.
Michael
Bruce
Nelson.
Destiny.
Good. You double it.
Destiny.
You right, you right.
You double it. You double that sum. All right. But who sees it? Leave his hoodie alone. That's enough. We double it, but we have a problem with that. Because this first drop, there was no up to it.
Yeah.
So we have to subtract out the up that didn't happen. We
Oh.
have to subtract out the no up right here.
So we need to divide by 2.
Okay? So how do I subtract out the no up? I have to take out a g sub 1. Yeah,
Wow.
a 5. So what we do is 2 times the first drop, which was 5 feet, 1 minus the ratio. It tells me the ratio is 8/9. That's a pretty good bounce. 8/9. All right, 6th bounce. 1, 2, 3, 4, 5, 6.
Wait, I'm over.
Over 1 minus the rate.
Is that?
Okay, so this part right here is what we did on Friday. That's what we did Friday.
Yes.
Wait, that's a 5, right?
Yes.
Okay, I was right.
Why is the 2 there?
Okay,
What does the 2 mean?
well, while you were being excited about drop top, I explained that because it goes up and down, we have to double it.
Oh, okay.
Right? And then we have to subtract out the initial because it didn't go up and down.
Yeah.
So, quick math.
All right.
That was quick.
So, I want to see if you can calculate correctly. Punch it in. See if you can tell your calculator what to
I'm gonna
do.
do this slow and steady.
So you take out the.
So, if you just
I'm still kind of stuck on the piece of it. It's like I'm not.
The reason we're subtracting out the first one,
Yeah.
this one had an up and down, an up and down, an up and down, an up and down, an up and down. That's why we had to double it.
Yeah.
Because all of these had an up and down. But the first one didn't have an up and down. It just had a down.
that.
And when we doubled it, we gave it an up. So because we gave it an up that it didn't have, we have to subtract out that up. that it doesn't have.
Okay.
That's why we subtract the 5.
14
plus 6.
Uh-oh. Wait, I think
That's
we
right here.
forgot a parenthesis.
You think I did?
Wait.
This should be a smaller parenthesis right there.
Doesn't it go with this after the 6?
Yeah.
Okay.
That's right here.
There we go. All right, and this is feet.
Yeah, feet.
Did you get that?
Oh, dang it. I was 5 off.
That's a shame.
Because you didn't add the 5 at the end.
Oh, yeah, I did subtract the 5.
Oh, I didn't subtract the 5 either.
Roasted!
I know, I didn't subtract the 5.
You're also 20
Oh,
off.
wait, and I forgot the 2.
You didn't subtract the 5, you're 20 off.
Gooey's like, Gooey, can you give me a boy?
What?
You just like look at people when they do math, they're just like, boy. Boy, your boy.
Yeah, I don't think about it. Math makes her cry. Carlos, I appreciate you coming to my meeting.
Oh.
Carlos, could you bring me the
Dance.
Preston.
Like an authentic one.
An authentic.
Because I don't have
He doesn't have suppliers. Carlos came to my track meet, and then it was like 8 o'clock, and I couldn't open my shoulders.
Yes.
No, not on my shoulders. He's on my back.
This is gonna sound weird on the
Didn't I give you piggyback ride? That's just out of Friday, didn't I give you piggyback ride?
I actually don't.
Remember you got up on my back to watch the race?
Oh yeah.
To see over my thing? Yeah. It was awesome.
Oh yeah, that was true.
Good.
And we went to breakfast at Preston.
Oh yeah, I like leaned him over and he was like, give me bread. And so I keep going. I took Carlos piggyback ride as well. You say Brooks? Calm yourself down, okay? Okay, what you're doing?
All right. I needed
What happened?
I needed this parenthesis because I had a parenthesis here that I opened.
Yeah, you gotta close the
Yeah.
parentheses.
So I had to close the final. Abby, this is where I led you astray. This one right here. Yeah, that's where I led you astray. All right. So part B. This has the total distance before it comes to rest. When you see comes to rest, what kind of sum is that?
What does that mean?
Infinite. This tells us the sum of an infinite.
Wait, if
it comes to rest though, can it be a finite?
It's like if it's coming to rest, meaning it's. I'm sorry, I'm
All
trying
right. So what we said was this is where theory and reality don't meet.
Okay, so
B is the theory.
don't
A
be
is the
logical.
reality.
So when it says comes to rest, that's infinite.
Okay.
Right. All right. But the same problem happens. We have the up and the down. So we have to double it, and then we have to take out the first drop that we doubled and shouldn't have. Okay? So we do 2 times g sub 1, which was 5, over 1 minus 8/9 minus 5.
Quick math.
You're right, Gooey.
Right.
And this should give you 85 feet. So if we continue to let the ball bounce till it stopped, it would have traveled 85 feet. All right, you try.
Oh no.
Oh, we're running out of time.
Yeah.
85.
It's no big deal.
90.
What?
This one's 90.
Oh, I say the feet.
I'll still solve it, but it's supposed to be 90.
It's the back. Homework is the back.
The whole back?
Those
Wait, Miss Will be the whole back?
What did he just say? He was resting.